Hi, welcome to our second training session, where we will demonstrate how we can easily design, build, and test LPC2148 based embedded system, which will drive 7-segment alphanumeric display. Any embedded system project involves 3 important steps. The first step, we select embedded C as our programming language. The second step, LPC2148 based evaluation board. And the last step involves procuring 7-segment display module. Programs written in C are readable and easy to debug. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. The most important component of our embedded system will be LPC2148, which functions as the brain of the system. LPC2148 has 32 kilobytes on chip SRAM and 512 kilobytes on chip flash memory. LPC2148 is available in a small LQFP64 package. It has 2 general-purpose I/O ports. Each I/O pin is multifunctional and can be programmed as input or output. Each of these I/O pins can be either digital or analog. ARM7 registers are 32 bits in size. ARM7 can read or write 32 I/O pins in one cycle. CPU register bits are directly mapped to individual I/O pin. I/O pins are terminated in group of 8 on a header. If we connect any peripheral to header 1, we use bit 0 to bit 7 of the 32-bit register. If we connect any peripheral to header 2, then we use bit 8 to bit 15. If we want to use header 3, then this header bits are mapped to bit 16 to bit 23 of the registers used. LPC supports crystal oscillator up to 30 MHz, a 16 MHz oscillator is wired to this demo board. A 5-volt dropout regulator provides 3.3 volt power to LPC2148. A reset switch is connected to LPC2148 reset pin number 57. A low on pin 57 causes processor to begin execution at address 0. On reset, every I/O port pins are configured as general purpose input pins. The USB Jaguar debugger is used to download program from the PC to the target. It uses ARM 20-pin connector. Seven-segment display is made up of 7 illuminating LED segments. By illuminating various combination of LED segments, alphanumeric characters can be displayed. During this lab, we will be programming LPC2148 to drive 7-segment module to display alphanumeric numbers. Port P0.0 through port P0.7 on header 1 drives 7-segment bits A through G on the peripheral board. In this section, we start with how to use Crossware Embedded Development Studio. Embedded Studio is capable of creating executable code for LPC2148. Using a new software is always complex for the first time. Any integrated development environment starts with the notion of a project. In essence, a project is a list of source file that all needs to be compiled and linked together to create an executable file. A project is what gets built, and without a project, Embedded Studio will build nothing. In addition to projects, Embedded Studio has the notion of a workspace. A workspace is a collection of projects. A large development activity can consist of several executables working together. Workspace is capable of displaying and modifying files from any project. Let us now create a workspace. This workspace will be a collection of all our individual embedded project. From menu bar, File menu, click on New. Go ahead to click on Workspace tab, select Empty Workspace. This opens up a dialog box wherein you can enter directory name and workspace name. Name the directory and workspace name as MLab. This opens up Integrated Development Environment and a workspace named MLab. So let us add a new project to this workspace. From the menu bar, select File, New Project, and select Executable Program option. This opens Target Selection dialog box. Select LPC2148 as the target processor. Once we have selected the processor, we then create a new project. We need to create a directory and name the project correctly as shown. The next setup requires us to configure the RAM and ROM size for the project. After reset, the ARM7 starts from location 0. The size of the ROM is 256 KB. The next dialog box selects the compiled output to be of 695 file format. This format includes the compiled hex code and debug information. Click OK to continue. The last dialog box selects the programming language and adds startup file to the project, if needed. The Embedded Studio then creates the startup file, a skeleton C program, and adds them to the project. The main screen of Embedded Studio is split into 3 views or windows. The first window is the project view, which shows all the files in the project. The second view is the code editor view. Here we can see the C skeleton file added to our new project. Now we can start editing the C program file. The last view is the output view. Here we can see the compiler messages. If one of view disappears, use the view menu to get them back. 7 segments display is an arrangement of 8 light-emitting diodes used for displaying alphanumeric numbers. The diode equivalent circuit shows all the cathodes, or negative terminals, of the segment LEDs are connected together and grounded. We can produce a truth table for each hexadecimal numbers. The animation displays the possible binary values when each individual segment is lit. The combination of the bits, or the truth table, is used by an embedded program to display hexadecimal number. We connect first 8 bits of an I/O port to segments A through F. While we connect bits 12 to 15 to cathode of each digit. To select a digit for display, the embedded program grounds the common cathode bit of the respective display unit. Once we write the truth table or load this data into an array, we can use the array data to display hexadecimal number on the fly. Before we actually code, we will use a simple flow chart to visualize the steps required to implement our second lab. On reset, the processor program counter R15 is set to 0. The compiler provided startup code is executed, and the program jumps to main routine. All the I/O pins on reset are programmed to be general purpose I/O, and all pins are in input mode. Hence, in the first function call, initialize LPC, we set the port direction of first 16 bits to be output. We need an integer variable, hex count, to be displayed on the 7-segment display. We have only 4 digits to display, and the hex count should reset when all 4 digits shows character F. The display count function uses each digit of hex count as an index to get hex value from the array and shows it on the selected 7-segment. The flowchart looks okay. Let us go ahead and code. Let us start building the C skeleton code. We add our first function call to initialize LPC. We then create an integer variable, hex count, and set it to 0. Our aim will be to display this count on the 7-segment display. This requires us to create an array where we can index and get segment values to display. Hence we call our last function to display segments. We will reset hex count variable, when count value surpasses 4 digits. We use the wizard to fill in the initialization code for our function, initialize LPC. The wizard creates a named pointer and uses it to set the direction of individual port pins. The last function call, to display 7 segment bits, is quite simple. Each digit of the hex count variable is treated as an index. This index now points to an array or lookup table. The index value provides the data for each individual segment. As our display module is common cathode, to illuminate a bit, the corresponding port pin has to be driven high. If index is equal to 0, then data 3F drives individual segment to show hexadecimal number 0. We can use the standard IO set and IO clear register to toggle any segment on and off.